Hello and welcome to this video about harmonics. We're going to look at harmonic series and the harmonic series of standing waves, harmonic series of a vibrating string, the harmonic series of open pipes, harmonic series of pipes closed at one end, and a few ideas that have to do with harmonics, timbre, pitch, and beats. Let's start out by talking about standing waves on a vibrating string, like this violin, for example. You remember that speed equals frequency times wavelength. We can rearrange that equation to talk simply about frequency of the wave on that string. Frequency is equal to velocity over wavelength. And we also can remember that the frequency is going to depend on the string length. Remember, the lowest frequency of vibration on a standing wave is going to be 2 times the wavelength. So we can substitute for the wavelength a 2 times the string length. We know that is going to be the lowest frequency of vibration on that standing wave. It's also the greatest possible wavelength. That is called the fundamental frequency. When we start talking about fundamental frequencies, we can also talk about something called harmonics. And multiples of the fundamental frequencies are called harmonics. For example, if the fundamental frequency is represented as f sub 1, we call that the first harmonic, and then the second harmonic is equal to 2 times that first harmonic, or that fundamental frequency. Then a harmonic series is simply a series of frequencies that includes the fundamental frequency and then integral multiples of the fundamental frequency. So this would be the first harmonic, which is just the fundamental frequency. The second harmonic is 2 times the fundamental frequency. The third harmonic is 3 times it. And the fourth harmonic is 4 times the fundamental frequency. Here is a chart showing what we've just talked about. However, it has the pattern of the standing waves included as well. You can visualize this a little easier. Here's the fundamental frequency. Here's the second harmonic, and you can start to see a pattern between these frequencies and the patterns in the standing waves, as well as patterns with the wavelengths necessary to create these different harmonics. So if we take all those patterns into consideration, we get a really nice little formula, an equation that describes the harmonic series of standing waves on a vibrating string. And when we're talking about a vibrating string, we can describe the frequency as equal to the harmonic number, which is 1, 2, 3, depending on which harmonic it is, times the speed of the waves on that string, divided by 2 times the length of the vibrating string. Let's do an example together. Let's say we have a little toy guitar, and one of the strings is 34.5 centimeters long. What's the wavelength of its first harmonic? Well, remember that the wavelength for the first harmonic is equal to 2 times the length of the string. So 2 times the length of the string in meters is 0.345. That's 0.690 meters. What if the string is plucked and we find that the speed of waves on it is 410 meters per second? What are the first 3 harmonics? Well, remember our equation for harmonics on a string. We have that right here, and we can simply plug values into that to find the first 3 harmonics. And for the first harmonic, the frequency is equal to 1, that's the harmonic number, times 410 meters per second divided by 2 times the length of that string. And you can see that the meters cancel out. I'm left with inverse seconds or hertz. We get 590 hertz. We can only have 2 sig figs, and that is the first harmonic. Frequency for the second harmonic is solved in the same way. It's 1200 hertz. And the frequency for the third harmonic we can see is 1800 hertz. So those are the first 3 harmonics for that string traveling at that speed. Now let's take a look at what standing waves are like in an air column. We have 2 different situations, and we're going to look at the differences between them. We can have an air column with both ends open. We have open ends here when air is going through this column. This is a column that has only one end open. So let's take a look at the situation where both ends of the pipe are open. If both ends of the pipe are open, we have an antinode at each end of the pipe. This is exactly the opposite of a string fixed at both ends, because if a string is fixed at both ends are nodes. But because the distance from one node to the next is a half a wavelength, it's the same as the distance from one antinode to the next. So the pattern of standing waves in this pipe that is open at both ends is going to be the same as that of a vibrating string. Here's the formula for the harmonic series of a pipe open at both ends. It is the same as that for a vibrating string. The length, though, in this case, is the length of the air column, and that's the only difference. For a pipe that is closed at one end, however, we have something very different. In this case, the closed end is a node. The open end, in this case, is an antinode. You can see how the pattern works in this situation. Because of this, not all of the harmonics are able to be present. Only the first harmonic, the third, and the fifth, in essence, the odd harmonics only are going to be present in order to obtain the node at the closed end and the antinode at the open end. So here is our nice equation for harmonic series of a pipe closed at one end, and n will only be the odd harmonics. Also notice that instead of 2 times the length of the vibrating air column, it's 4 times the length of the vibrating air column in the denominator. So let's say we have a tuning fork, a clarinet, and a viola, and they're all playing the same pitch, the same fundamental frequency, which determines the pitch, and they are playing at the same volume, same intensity. Why do they sound so different? Let's take a look at what's going on. When a tuning fork vibrates at its fundamental frequency, that's all it vibrates at. It's the fundamental frequency. There are no other frequencies at which it vibrates. The waveform of these instruments, though, is more complex because they also consist of many harmonics. So they do not just vibrate at the fundamental frequency, but they also have these other harmonics, and each of them is at a different intensity. And so when we combine, according to the principle of superposition, these different waves, we get the resultant waveform here, and it's going to look different because each individual harmonic waveform has a different frequency. So this explains why these sound so different, and that sound quality has a special term called timbre, and it simply describes the mixture of harmonics that are producing the characteristic sound that we hear for an instrument, and that's called timbre. Have you ever listened to instruments that are slightly out of tune with each other? You might make a face like this. We're going to look at something called beats. What are beats? If we have 2 slightly different frequencies, right here, there's one in light blue and one in black. They're traveling in the same direction, and their superposition is going to be looking like this. We're going to end up perceiving that as a variation in loudness, and that's what we call a beat. You can see that when we apply the law of superposition, we end up getting a resultant wave that looks like this. This is the interference pattern formed, and we can see here we have perfectly destructive interference. Here we have constructive interference. Right here we're getting 1 beat. Right here where we have the constructive interference again, we're getting 1 beat again. So we can see that when these 2 individual waves are in phase, that's where we get the constructive interference and we get the beat. When they're perfectly out of phase, that's where we see these nodes. Beats can also tell us how close together the fundamental frequencies are. If the beats heard each second decreases, then we can know that the 2 waves are closer to being completely in phase at all points. Here's some advanced ideas. Try the optional lab with an open-ended resonance tube and a closed-end resonance tube, and see if you can find the length of pipe that produces the loudest sound for each of those pipes. Also, have you ever noticed how sounds in an empty room are really different from sounds in a room that are filled with all of your stuff? Why is that? What's going on? What is reverberation? Find out ways that music halls or auditoriums are constructed to reduce reverberation. Look forward to seeing what you come up with, and we'll see you in class.